start over.
So let's work on this problem. The framework is supported by the member AB, which rests on the smooth floor. When loaded, the pressure distribution on AB is linear as shown. Determine the length. It's not in your note packet. See you all shuffling, and I realized I only had one in your note packet, and I want to do another one. Okay? Okay, so determine the length of member AB and the intensity W for this case. Nah, that's not a good two-force problem. Let's choose a different one. So, I mean, let's talk through it though. Okay, we can talk about this for a second. Is D6? Yes, it is. Why is D6, Jordan?
Because the top beam that's applying the force is 2/3 of D.
Okay, yeah, so Jordan's saying, look, you got 800 pounds going down here, and if we know that we have this distributed load here, then it's that 1/3, 2/3 thing. And so for it to be in equilibrium, I need the resultant to line up right underneath it, right? And so he says, wait, I need 2/3 to be 4, so 6, right? 2/3 of 6 is 4. So he's saying it's 6 long. Then what would the intensity of W here have to be? Let's see, 1200 times 6. No, I don't think so. So whatever it is, we need to multiply it by 6 and divide it by 2 and get 800. So multiplying by 6 and dividing by 2 is the same as multiplying by 3. So it should be 800 divided by 3. 233? So if this was 233, and I multiplied it by the length of 6, and then divide by 2, do you get 800? Two? No. I think it's 266, isn't it?
Yeah.
Not 233?
Yeah. I
Yeah.
saw that and I was like, I actually spaced
So
out.
try 266 times 6 divided by 2.
Wait, did you
Yeah.
get it in register then? That was
Okay. All right.
You're not even
So then let's look at this. Okay.
I was like, oh, I need to find 1/3 of that. What that
Here's a
was.
nice crane. Okay, 536. Outriggers A and B are used to stabilize the crane from overtraining when lifting large loads. If the load to be lifted is 3 megagrams, we're just going to use a picture. I don't like the problem. Which of these are two force members? Is the boom?
No.
Why is the boom not, Rebecca?
Multiple forces along that line.
It's got a force out here. It's got a force here. And it looks like it has some mass, right? What is a two-force member here? The cable from here to there, two-force member. Okay? You guys feel pretty good about what a two-force member is and how it helps you? Okay. 2 application points. 2 points of application. Okay, yeah. So Nate's asking, would A to B be a two-force member? No, it wouldn't. You would know, though, at A you just have vertical, and at B you just have vertical. Right? Okay? All right. So then we can move along here. We're going to look at equilibrium in 3 dimensions. Okay? And remember how when we looked at equilibrium in 2 dimensions, we had a couple pages of connection types. Well, guess what? We have a couple more pages of connection types in your book. Okay? And again, the rule is you really need to think about what types of motion is the connection type designed to restrict. Okay? So here's a super common thing you see all the time. This is called a single journal bearing with a square shaft. I've never actually seen one of these. It has a square shaft that can slide along this thing. So it's really designed for 5 unknowns, okay? It's going to prevent motion in Z and X, right? It will allow it to slide in the Y. It will resist a moment about the X-axis, about the Z-axis, and about the Y-axis, right? So I have 5 unknowns for this type of joint. A single thrust bearing, and this bothers me. I don't think this is, when you actually take a machine design class, they would say to never treat a thrust bearing this way, okay? Because right now this is saying that bearing, if this was a single bearing in here, they're saying that it would resist a moment about the Z-axis, which is incorrect. You would never have a single bearing that does that, right? You would use 2 bearings separated by some distance, and you wouldn't ask them to take a moment, right? So like your wheel bearing, anyone ever taken apart the wheel bearing on a car or a trailer or anything? Right, so your wheel on the front of your car has what's called a spindle, and it's shaped something like this usually. Okay, except this is equal in size. Okay, and the way a wheel bearing or your wheel spins on the car is there's actually a bearing that's located right here. It's the inner wheel bearing. So your car is sitting on this side, right? So your car's over here, and this is your wheel hanging out here. There's a bearing that goes here, so has balls, or they're tapered roller bearings. So they have these little tapered rollers, okay? And then there's some space, and then there's an outer wheel bearing that goes on right here, usually also a tapered wheel bearing. And it's tapered in the opposite direction, okay? And then these, so what I'm drawing here, if I did it in perspective, right, you've got one bearing like this, okay? And the spindle comes through it and steps down, and then you'd have a smaller bearing like this, okay? And these are mounted in then kind of what holds your disc brake and your or your brake drum if you have a really old car, right? And then the lug nuts come out here, and you bolt your wheel on, okay? So this is the spindle and then there's a big nut right here that you tighten that sets the what's called preload on your wheel bearings. So this is the proper way if you want a bearing to take out a moment load. These bearings now, you only count on them resisting load in this direction. What the book is stating here, where they say a single thrust bearing here, they're saying, oh yeah, I could design this with just having a shaft that comes out like this with one bearing on it, and then I could allow this bearing to keep it from twisting like that, from twisting sideways, which is terrible. You would never ever do that as a mechanical engineer. So, don't ever, yeah. Anyways. Well, no, you can trust the book, but just know that if I see a single thrust bearing, I'm probably not going to say that it resists any moments. It just does forces in my mind. But to solve some of the problems in the book, you might have to say it resists moments, okay? A single pin, again, they're going to say, well, it resists a moment about the Y and the Z. Not really. I mean, if you had a pin joint like that with a big long lever arm and you pulled on it, you'll just shear that pin right off. That's not what it's designed to do, okay? But you get the idea. We have unknowns, and we need to think about those unknowns and quantify them, okay? So back to your note packet, and we'll skip that first one and go to P5-2, okay? Where we're asked to draw the free body diagrams of each of these. Okay. So, what do you think in 3 dimensions the resultant force of a ball bearing is going to be at A here? Brendan's pointing up at the ceiling, and he's right. It's just going to be a normal force at A. Okay? What direction is that normal force going to be? Perpendicular to the surface, but in this drawing, what direction is that? It's the Z direction, so we could say it's in the K hat, right? And it looks like C is maybe a ball and socket joint. So a ball and socket joint resists motion in X, Y, and Z, but allows rotation in all three directions. Right? So we'd have some force at C in the X, some force at C in the Y, and some force at C in the Z. And B, again, would just be a normal at B in the K hat direction. Okay, what do you think about a bearing? So I told you we're not going to do any moments in bearings. So this bearing at A, what directions does it resist motion in? X and Y, yeah. So we'd have some A sub X and some A sub Y. How about at B, what directions does it resist it in? Excuse me? In the X, B sub X, and B sub Z. I agree with that. Okay. And how about at C? CY and CZ. So do you see why it's CY? Come on. Thanks. Thanks. Okay. Okay. Kind of get the idea of doing the free body diagrams? All right, so here's the thing. When we change from 2 dimensions to 3 dimensions, the conditions for equilibrium stay the same. It's just we're thinking about vectors more now. So we're going to say the sum of the force vectors has to be 0, and the sum of the moment vectors about a point has to be equal to 0. Okay? We can further break this down. So this is probably going to mean that, well, the sum of the forces in the X equals 0, the sum of the forces in the Y equals 0, the sum of the forces in the Z equals 0. The sum of the moments about the x-axis has to be equal to 0. The sum of the moments about the the y-axis has to be 0, and the sum of the moments about the z-axis also has to be 0. How many equations is that? Looks like 6. So I can now solve for 6 unknowns. Okay? So let's flip back a page and try one of these. So we've got this pipe, right? What would the, rather than trying to redraw this, I'm going to draw my free body diagram right on it at A. What types of motion does A resist? It's called a fixed connection. It resists them all, right? So I'm going to have some forces like this, right? So I'll have A sub Z, A sub Y, A sub X. And then I'll also have some moments that I'm going to draw in the positive direction. This would be the moment about the X, the moment about the Z, and the moment about the Y. Okay, so let's start with some of the forces in the x direction has to be equal to 0. And we're going to say kind of down in this way is positive x. So it looks to me like we're going to have A sub x. Anything else in the x direction? Minus 400 newtons equals 0. So I'm going to go with A sub x is equal to 400 newtons. Okay. Sum of the forces in the y equals 0. Y is kind of down and to the right. Looks like I'll have AY plus 500 is equal to 0. So AY is equal to negative 500. Then I'll have sum of the forces in the z is equal to 0. Straight up being positive. Looks like I'll have AZ minus 600 equals 0. So it looks like AZ is 600. Everybody okay with that? All right. So then let's sum the moments about the x-axis and say they're equal to 0. So that's going to be positive this way. What causes a moment about the x-axis? Well, my reaction force mx does, and it's in the positive direction, right? So I've said that there's this mx reaction at A, that A resists rotation about the x-axis because it's fixed. So because of the connection type, I have mx here. What else causes a moment about the x-axis? Does the 400 newtons? No. Does the 500? Does the 600? Okay. So the 500 does. So is it positive or negative?
No, negative.
It's negative 500 newtons times what's the lever arm going to be? Is it 1 meter? It's the it's 1.25. It's the other direction, right? It's the vertical distance off. So we need to find the perpendicular distance from the line of action of the force. So the line of action of the force runs this way. So that means it's going to be this way that we need to find the distance. So it's 1.25 meters. Now, 600 newtons, negative, right? Can everyone see why I'm saying it's 600 newtons negative? Because here's the x-axis, 600 down, so it's going in the opposite direction. And this guy, the distance would be 1 meter. And that all has to add up to 0.
Can you explain why you have the MX as the extra value?
As a, excuse me?
Like, why did you put the MX there?
Yeah, so this mx is just the magnitude of this reaction moment, right? So A is a fixed point, and so it's going to resist rotation, and I just assumed that it went that way in the positive direction for the analysis. Okay? All right, so it looks like I could solve this and say that mx is equal to 500 times 1.25 would be 625 plus 600, 1225 Newton meters. Okay. So how about you do sum of the moments in the y direction equals 0? I think there's going to be two forces.
think if there's a force in the z and you're talking about the y, you're going to take the x distance.
Okay, so if I sum them in the y, I'm going to start with my my because I'm assuming it's in the positive direction. Then I have 400, which appears like it's going to cause a negative, so it'd be minus 400 newtons times its height of 0.75 meters. Looks like 600 is also going to cause something, and it looks like it'll be negative, also with a distance of 0.75, and that'll have to equal 0. So we'll have 300 plus 450, so that's 750, I think. My is equal to 750 Newton meters. Okay. So then the last one to do is to sum the moments about the z-axis and set that equal to 0. And the only thing I see that acts in that axis is m sub z. So it must be equal to 0. Right? Because the 400 newtons line of action crosses the z-axis. The 500 newton goes through the z-axis. And the 600 newton is parallel to it. And therefore it doesn't cause any moment about it. All right? So what we've just done is essentially a scalar analysis of a three-dimensional problem. Right? How this will change going forward, let's flip a few pages forward. We won't have time to do it today, but you could see here, if you go to 570, this stiff leg derrick, they call it.
Sounds like an old cowboy name.
Yeah, sounds like an insult to somebody. You stiff leg derrick. Okay. So to do this, I think what we're going to end up doing is we have a ball and socket joint here, right? So a ball and socket joint, we said resists loads in the x, the y, and the z, but no moments. So then the moments have to be taken out by this cable BC and BA, right? So this will get funky, right? We're going to have to do cross products and break it into I and J, K, and all sorts of good stuff, okay? We're going to stop here. What I'd like you to do for the weekend is practice those two-force member problems. They're really fun, right? Because they're actually, they're really applied. They aren't made up. They're really applied, real-life situations where we use two-force members in design. So I want you to get good at identifying them because we're going to finish this up on Monday and then move into structures and machines, which is all about knowing where two-force members are. Okay? So we're going to be doing trusses and things like that starting next week. Okay? So please, please practice. Practice, practice, practice.
In force members, doesn't matter the type of connection points, it's just that there are two connection points.
Good question. So Nick's asking in two-force members if it matters what type of connection point it is. And it does actually, because if you had, they have to be pin connected essentially. If you had a fixed connection, right, and then just a load out at the end, that fixed connection, so what I'm talking about is if I had a beam that was cantilevered out, right, like this, and I said I put a force there, we could say, well, there's a force applied here and a force applied there. It's a two-force member. It's not, actually, because this has moments and a bunch of other reactions. So they have to be pin connected. Great question. Okay? All right.